Welcome back. We are starting Unit 9.1, and this is on reaction kinetics. And in the books that I sent you, this is going to be book 2, and it's going to be page 2 through page 44. And I know that seems like a lot. That's like 42 pages, but it's just a little bit of here and a little bit of there. So it's not the entire 44 pages. It skips around a little. So go ahead and read that. Reading this and looking at this in this book is going to really help you with this. All right, so what is reaction kinetics? Well, the word kinetic means to move. So reaction kinetics refers to how fast a reaction proceeds, the rate of the reaction, how fast the reaction goes. And not all reactions happen at the same rate. For example, sodium, metal, and water. So if you put sodium metal down in water, you're going to see a very violent, quick reaction that releases a lot of energy, a bunch of energy all at once. And this sodium metal reacts with this water and produces fire very quickly. There are some videos on YouTube that you can look and watch where they do bigger chunks of sodium. This is just a very small piece of sodium in a dish of water. So that happens very quickly. And compare that to rusting of an iron nail. So if you put an iron nail down into some water, and it could be salt water, it could be plain water, that's going to change. Those ions are going to change the rate of reaction. So rusting happens over days, maybe weeks, maybe months to happen. So that's a very slow reaction. The comparison that he uses in your book is the comparison between a firecracker. So when you light a firecracker and it explodes, that is one violent, very quick reaction. All of that reacts very quickly, less than 1 second. As compared to eating a sandwich and getting the energy from that sandwich, it sustains our body and gives our body energy over hours. So it doesn't release that energy all at once. We sustain that energy over hours. And it compares that again to the rusting of a bicycle. All right, so rusting happens over matters of weeks or months. So different reactions have different rates. So let's take the example here of driving. That's a rate, a speed. So we're driving from Aubrey to Space Center, Houston. And that is, according to Google Maps, 314 miles. And it gives an average estimate of how long that should take is 5 hours. So if we look at just the total mileage over just the total amount of time, that's going to give us an average rate. So the change in quantity, which is the change in miles, over the change in time, it's going to give us miles per hour. And that's how we measure when we're driving, our speed that when we're driving. So let's look at that and see what our average speed is going to be. All right, so we have our calculator here. We're going to use that. So it was 314 miles divided by 5 hours. So our average speed, let's get a decimal, is going to be 62.8 miles per hour. Okay, so that is going to be 62.8, and this was miles per hour. All right, so we know that when we pull out of the parking lot there at Aubrey High School and we're on Spring Hill Road, we're not going to go 62 miles an hour down to the red light. That's ridiculous. Officer Collins would have a problem with that, and as well he should. So what we do is we break this down into increments of time. Now you can break this down into minutes, like 1 minute, 2 minute, 3 minute. That's a lot of data points that you're going to have over a 5 hour. Or as we did in this table, we break it down into half hours. So the first half hour, we're going 14 miles. All right. So we started off at 0, right? And I'm just going to put that up there, 0. For the first 30 minutes, we went 14 miles. Okay, and the time here is a half an hour. So that's going to be 0.5 hours. So if we look at that, just that first half hour that we're driving, okay, so 14 divided by 0.5, we're going to see that our speed was 28 miles per hour. And that's just for that first 30 minutes. So 28 miles per hour. And that makes sense because, we leave the parking lot, we're on that little bit of part of Spring Hill Road, and then we're going to turn, left there. We're not going to go north. So we want to turn left at that red light and go down through the road that's in Aubrey. I don't know the name of it. But, there's traffic lights there. So we're going to be going pretty slow, right? So let's look at our first hour. So if we just take the first hour, let's say it's 0 to 1. Okay, so that's 1 hour. Okay, and in that 1 hour, we went 45 miles. Okay, that's 45 miles per hour. So we increased our speed a little bit, and that makes sense because there's a bigger distance with no red lights and no stop signs after you get outside of Aubrey and after you get through the traffic, people turn into their subdivisions. So that makes sense. So let's look down here. Between this 2.5 and this 3, we should be on Interstate 45, and we should be going pretty fast there because it's open road on an interstate. So let's just look at that. All right, so what did I say here? This one? Okay. So between 2 and 2.5, we did a 0.5, right? And 140 to 170, that is 30. Okay. So if we take 30 divided by 0.5, all right, so that's 60 miles an hour. And that makes sense because we're out on an interstate, maybe driving faster. So you can see that there's a difference between average speed or average rate and then instantaneous. So here it was 28, here was 45, here is 60 miles an hour. So we can get different rates depending on the distance or how far you are into the trip. So that's the same thing with reactions. Reactions may start very slow. Reactions may speed up in the middle, and then they're going to taper off at the end. Okay, and the reason for this is because there are factors that affect the rates of the reaction. We're going to talk about some of those. All right, so this is the rate of the reaction, the factors that affect the rate of the reaction. You're going to have surface area. So here we're talking about sugar cube as opposed to ground up sugar like granulated sugar or powdered sugar. Now, because there's a lot more surface area, it's going to dissolve or go into solution quicker than if it was a chunk. That's just like if you take a peppermint, an average size peppermint, you grind it up and make a powder out of it, and then you put that in your mouth. It's going to dissolve very quickly, and within the matter of seconds, it's going to be all dissolved and you can swallow that, right? But if we take a whole peppermint that's not been ground up and we put it in our mouth, it's going to be like 5, maybe 8 minutes before that dissolves and goes away. So surface area does affect the rate of the reaction. Okay, another thing that affects the rate of the reaction is the concentration of the species. For example, here is a very elementary experiment, and this is using the density of water mixed with sugar. So here we have a lot of sugar mixed with water. It's dense. So when we put it in this graduated cylinder, it's going to be at the bottom. And then the second layer is a little more water, a little less sugar. So that sits on top of this one. This one's just a little bit less. And then this top one is just water, no sugar mixed in it at all. And so what's going to happen is initially these are going to come out into different areas like this. It's going to separate out, not mix together. But what's going to happen is because this is a higher concentration of water than, say, the blue and the green, because this is a higher concentration of water, and water is what's dissolving the sugar, these two are going to mix together first. And then once these mix, then these will mix. This next layer that's going to mix is going to be the blue with this, and then eventually the purple with this. So these two layers aren't going to mix as quickly as these two layers because the concentration of water, that is the solute, is going to dissolve this layer first. Okay, and eventually we come back the next day, this is going to all be one color. But this is going to happen first because the concentration of the water is higher. And another thing that affects the rate of the reaction is the temperature. So when we increase the temperature, we're increasing the kinetic energy, and then that is going to make the reaction go quicker. And we're going to look at this in a lot more detail. So it bears to mention now that there is such thing as called a catalyst. I want you to write this definition down. A catalyst is a substance that increases the rates of the chemical reactions without being used up in the reaction. We're going to talk more about catalysts, not in this course, but in AP chemistry and the effect that the catalyst has on the reaction. Okay, but there are such things as catalysts that change the rates of the reaction, but don't become part of the reaction. All right, now all of this is based on what's called the collision theory. Okay, in the collision theory, in order for a reaction to even happen, there are three things that must take place. And I want you to write these down. In order for a reaction to happen at all, now we're not talking about the rate of the reaction. Okay, we're just talking about for it to happen at all. One thing is that the molecules must collide. They have to come in contact with each other. So when we look at a chemical equation, we have A plus B yields AB. In order for that to happen, they have to come in contact with each other, and that's a collision. Okay, the next requirement is that they must collide with enough energy to break the bonds and reform new bonds. Okay, so when they collide, they must collide, but when they do, they have to have enough energy to actually break bonds and reform new bonds. Okay, and we look at that like striking a match. Okay, so those chemicals that are in the tip of that match are touching each other, right? They're colliding, but they're not colliding with enough force to break the bonds. So we have to put some energy into that chemical to make it react. So that's why we take that little strip of sandpaper that's on the side of the matchbox or on the bottom of the book of matches, and we rub the match across that. And what it does is it creates friction, right? Friction is heat, and that heat creates enough energy so that those bonds can break and reform. And then so the match is going to burn. Those two chemicals are going to combust. All right, the third requirement for a reaction to happen is they must hit or they must collide in the correct orientation. That means that it's like a puzzle piece. They have to be lined up just so when they hit each other so that those two pieces of the puzzle can fit together. Because if you, like you're putting a puzzle together, if you turn the piece, no matter what you do, those are not going together properly. Okay, so they have to collide. They have to collide with enough energy to break and reform bonds, and they must collide in the correct orientation. Okay, so those are the three requirements for a reaction to happen. Now we can speed up or slow down that reaction by doing one of these five things or a combination of these five things. Okay, and so those are, number one, you increase the concentrations. So if we just have one molecule of A and one molecule of B, and we put them together, what is the likelihood that they're going to find each other? Okay? And we're going to see examples of this here in just a moment. But if we have 100 of A and 100 of B, and we put them in a container, we're increasing the chances that those two are going to find each other. So we're increasing the concentrations. The second thing is increase pressure. And we're not going to talk about pressure in this section. We're not going to deal with pressure, but increasing the pressure is going to increase the speed of the reaction. Okay, because think about it. When we're talking about gases, if we increase the pressure, we're decreasing the space between the molecules. And so they have less distance to travel to find each other. So that volume is going to decrease, making it more likely for them to find each other. Okay. The third thing is increase the surface area. And we already talked about that. The peppermint, grinding up the peppermint, we're increasing the surface area. So it's going to increase the speed of the reaction between the saliva in your mouth and the melting of the sugar. Okay, another thing that we can do is increase the temperature. When we increase the temperature, we're adding energy. They're going to move quicker, and they're going to find each other more often, so that these three things can happen for the reaction. And another thing is add a catalyst. Now, we said just a moment ago that a catalyst is a chemical that it increases or it affects the rate. It could decrease it, but it doesn't become part of the reaction. We're also not going to talk about catalysts in this section. That's, again, a topic for AP chemistry. So we're going to look at these three things here, not so much surface area, in the demonstration that I'm about to show you to increase the speed of the reaction. But before we do that, we need to write down some more information. So the reaction rate, the rate of the reaction is directly proportional to the product of the concentrations of the reactants. So what does that mean? That means we have a formula for that. So the reaction rate is equal to the proportionality constant, which we're going to call K here, K for constant, of the concentration of the reactant. So here we have concentration A to this power, concentration B to the Y power. Okay. This relationship above is called the rate law. All right. So this is called the rate law. The proportionality constant in this case is called the rate constant. So that's K. And every reaction has its own unique laws and its own unique rate. So every reaction is going to have a different rate and it's going to have a different rate law. And for many reactions, the exponents X and Y are equal to 1. For many, many reactions, they're equal to 1. All right, so the values of X and Y are called reaction orders. Orders, okay, so there's a lot of vocabulary we're going to need to keep straight here. This is the reaction orders, the X and Y. We're going to find out how to find those. We're going to concentrate on first order reactions for a while where X and Y are equal to 1. And there are second and even third order reactions. All right, so the rate of the reaction depends on two things: the number of collisions per unit time, right? And the fraction of collisions that successfully produce a product. All right, so let's just recap. The molecules must collide. They must collide with enough force to break the bonds and reform new bonds, and they must hit with the correct orientation. So let's look at that real quick. We have a demonstration here, and this demonstration is found online. You can find the same demonstration, and all you have to do is go to PHET, Google PHET, okay, and it's going to come up with the right here, phet.colorado.edu. Okay, and all I do is choose chemistry here, and they have all of these demonstrations for concepts in chemistry, and we have looked at some of these. I know we looked at the ones for radio waves, and I know we looked at the ones for, let's see, what was it? Oh, gases, when we did gases. Well, there's one here on reaction rates right here, and so that's what I loaded. And so we have this ready to go here. All right. So in this demonstration here, we have A, which is going to be represented by the yellow sphere, plus BC molecule, which is the blue purple here. And this is when it reacts, A should react with B to produce AB, and then C is going to be kicked out. All right. So just to recap, they must collide. So if I take this, and this is just like a shooter like a pinball machine. You can pull this back and it's going to shoot, okay, the A to B. So let's just pull it over here and see, it doesn't collide, so there's no reaction. Okay, ooh, almost. All right, so there it collided, but there was no reaction. Okay, because all we did was just satisfy, let me pause this. All we did was just satisfy this requirement here. But we have two more requirements. So not only does it need to collide, but it needs to collide with enough force to break the bonds to reform new bonds. Okay, let's go back and look at this. Let me reset this launcher. So it must collide with enough force. Okay, so there you go. They collided, but it wasn't enough force. So let me show you over here. Here we have a graph, and this represents the energy and the reaction coordinate. So right here, this peak right here is called the activation energy. And we have to have this much energy in order for this reaction to happen. So it's like pushing a ball up a hill. Push, 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 push. And when you get to the top of the hill, now it has enough energy that it can roll down. We don't have to push it anymore because it's at the top of the hill. So what we're going to do is we're going to raise the energy. Oops. I think we have to launch it first. Okay, so, okay, so as we pull the plunger back, the energy goes up. So that tells us the amount of energy. So if we pull it up, see, it doesn't matter where we pull it. If it's below that activation energy, that's not enough energy to activate the reaction, so it's not going to happen. So if we pull this back so that we have enough energy, it exceeds that hump, and we let go, then we have this reaction. So A reacted with B and produced C. Okay. Now, also, we can do enough energy like this, but if it's not the correct orientation, it's not going to react, and I missed. So let's try that again. If it's not the correct orientation, it's not going to react. Okay, so see, it hit, and I had it pull back for enough energy, but our third requirement is that it must hit with the correct orientation, the puzzle piece. Okay, so it has to hit, and it shows here a straight line. So it has to hit straight on for this to happen. Okay. All right. So if I pull this back and it hits straight on, let's just do enough energy, just enough energy, then it's going to react. And see, it did. All right. So now let's change the rate of this reaction. Okay. So I'm going to launch this, and it's not going to hit, but see, within a few seconds that did hit and made the reaction. So that's really not what I wanted. So let's do this again at a different angle. So here we have this, and so finally they meet, but it's not, oh, they didn't meet. So we could sit here for a while, and this is going to go back and forth. So there they did meet, but it wasn't the correct orientation, so it didn't react. So let's wait. All right, they hit again, but it wasn't the correct orientation, so they didn't react. All right, they hit again, but didn't react. So we could sit here for actually quite a while and not see a reaction happen. So how do we increase the rate of this reaction? Well, here we have the second tab where this was a single collision. Now this is many collisions. So if we look back, we can see here that we increase the concentration is going to increase the speed of the reaction. So if we go back to here, and let's say that we have, let's double it to 2, and we have 2 of these molecules. All right, so let's raise the energy by heating it up till it's above the activation energy, and we had a reaction. Okay, so we had one reaction, and that was pretty quick. Okay, so now you see this blue and purple hit this yellow, but it wasn't it. Oh, so I'm sorry, we have this yellow and purple, and this yellow and purple should hit this blue one and go backwards, but it has to hit with enough force and the correct orientation for that to happen. And there it hit again, but it didn't happen. So we got one reaction there pretty quick, but okay, so now it did happen. It went backwards. So now we have the blue and purple and the two yellow. Okay, so if we increase the concentration just a little, then we can increase the rate. And it didn't increase very much. It was only a slight increase in the rate. But if we increase a lot concentration, let's say 10, okay, and we increase the 10 of these, and then we add enough energy for reactions to happen, okay, right there. All right, so we've increased the concentration and we've increased the energy. And so we saw one, there's one right there, there's two. Okay, and it can go backwards. There's three. Okay, and it went back to two and then up to three real quick. And because this is an equilibrium reaction, it can go backwards and frontwards. All right, so there you go. See, now we have 5 total reactions that have happened. So if we increase the concentration again, this should go a lot faster. So let's increase 20 and 20. All right, so 10 reactions, 9 reactions. Okay, it happens much, much faster. Okay, so let's do 50 and 50. Okay, and oops. Why didn't it do the other 50? Okay. Huh. Let's try that again. All right, so that's a lot of clicking. Let's just do 40. Okay, and let's just do 40 here. All right, so now we have 40 of each. Now let's raise the temperature to exceed and some of it's reacting already before we get to the activation energy. And so see, now we have 20, 17, 20. Okay, so you can definitely see by increasing the concentration, you're going to increase the reaction rate and the likelihood of these finding each other in the correct orientation. Okay, so let's look at increase the surface area. All right, so we really can't increase the surface area because it's just on a molecular level, one molecule to one molecule. But you see here, we did increase the temperature, and that did increase the speed that they react. Okay, so this is a good little demonstration, and of course you can go and you can play with this demonstration as well. Okay. All right, so all of that, we can use now what we know about reactions and this reaction, this equation here, okay, where we have the reaction rate, this rate law, and we can now calculate the order of the reactions, and we can calculate the constant for the reaction, and we can also calculate the reaction rate. And the way that we do that is through experimentation. So here in this experiment, we had 3 trials, okay? And this is just the reaction of A to B to create C. So very, very simplified reaction here to start off. What we're going to do on trial 1 is we're going to have both of the concentrations of A and B the same. So we have 0.0040 concentration moles per liter of A and the same concentration of B. Okay, we're going to put them together for a certain amount of time, And then we're going to measure the concentration, the rate that we get that these react. Okay, so that's going to be trial number 1. Then on trial number 2, we're going to start over. We're going to do a different. This time, we're going to have B stay the same. See, 0.004. We're going to hold B the same. Then we're going to increase the concentration of A. So when we double the concentration of A, but we leave B the same, here we have a different rate. Okay, so it came out that the rate increased. It actually doubled. Then we're going to have a third trial where this time we're going to hold A the same, 0.004. A is going to remain the same. We're going to increase B. When we increase B, we're going to get a different rate of the reaction. And so for this very simple reaction, we have to have at least 3 trials, because in trial A, they're equal. Okay, so for 2 reactants, they're equal. Then we're going to change A where B is the same. Then we're going to change B where A is the same. And with just these 3 trials, we can come up with a rate of reaction, and we can also solve for the rate constant. Okay, so here K is the proportionality constant. We can determine the reaction orders and with respect to each reactant in the equation. So with respect to A, changing A, we can find the order. And then we can find the order with respect to B, and then get the overall order for the overall reaction. All right, so here's how we do that. So we take rate 2, which is 0.020, over rate 1. Okay, so we're taking a proportion here. So rate 1 is where they're both the same. And so rate 2 is what's changing. So it's 2 over 1. All right. Then we're going to take and we're going to substitute in values for here. So if we take this rate over this rate, and that's what this is going to be equal to this rate 2 data over rate 1 data. All right, so K is the same. We don't know K, so we're going to put in K here. All right, so A, rate trial 2, A is going to be 0.008 moles per liter right here, times B. Okay, so B is rate 2, 0.0040. Okay, and it's to the X and to the Y. And then we're going to put in rate 1. So rate 1 is 0.0010 is equal to, okay, so A, 0.0040, substitute in B, 0.0040 here. So this is rate 2 over rate 1 set up. All right, so let's look at this. It's going to cancel this because what's on top cancels what's on bottom. They're the same, right? Okay. K is going to cancel K. So this is really what we have left over. So if we have 0.0080 divided by, to the X, divided by 0.0040, if we put that in our calculator, we're going to see that we're going to get 2 to the X, 2 to the X. And if we take 0.020 divided by 0.10, divide this, the units all cancel, okay? We're going to get 2. So 2 is equal to 2x. So if we solve for x here, x is going to be 1 because 2 to the 1 is 2. So for this reaction with respect to A, since A is what's changing, we're holding B the same. A is what's changing. So with respect to A, this is a first order reaction, okay, because x is equal to 1. All right, so we're going to do the same thing now, only we're going to hold A the same, and we're going to change B. So which A right here, 0.0040, and this one, trial 3, A is going to remain the same, where now we're changing the concentration of B. So we're going to do the same thing, only with changing the concentration of B. So it's going to be the rate 3 over rate 1 is equal to the reaction order here, the reaction law for 3 over 1. So if we substitute in our numbers the exact same way, so we're going to take 0.040 here, divided by the rate here, 0.10, 0.010. Okay, it's going to be equal to, so this is rate 3 for A. I'm sorry, trial 3, right? Rate 3 for A. So this is going to go here. Okay. B is going to go here. All right. And then for trial 1, these are the same. A and B are the same. We're going to substitute those in. All right. So K is going to cancel K. This whole thing is going to cancel this whole thing because it's the same. So what we have is just this. So 8 divided by 4 is 2y. 0.040 divided by 0.010 is going to be 4. 4 is equal to 2y. So if we solve for y, y is going to be 2. So in this reaction with respect to B, the concentration of B, this is a second order reaction because we got a 2 there. It's a second order reaction. So if we take information from comparing 1 and 2 and information comparing 2 and 3, we're going to come up with the reaction rate for this reaction is going to be this law right here. Proportionality constant, A, it was a first order reaction. So we really have a 1 there, but we don't write 1s. B, 2. So the overall order for the reaction is the sum of the orders with respect to each reactant. So we're going to add 1 plus 2. So in this case, for this reaction, the overall reaction order is a 3. So this is considered a third order reaction. So that's how we get that. Okay, so if I were to ask you on a problem or a quiz, I'm going to give you a data table like this, and I'm going to say, with this data, what is the overall reaction order? You're going to have to do this. So it's comparing, holding the trial where these are the same, then changing A, then changing B. Now we could have a third reactant. So we're going to compare A, B, and C reactants. Okay, this one only had 2. All right, so from that, when we get the reaction orders, so once you know the reaction orders, we can determine the rate constant, which is K, because now we have everything but K. We have, looking back at this, we have our overall reaction rate. We have the reaction order. This is 1 and 2. We know these concentrations, so we can rearrange this to solve for K now, the proportionality constant. All right, so if we rearrange that law there, we get K is equal to the reaction rate over the reaction orders. Okay, the resulting units are going to be different for every reaction. So this is where we're going to have to really, really pay attention to what our units are. Okay, and so 0 order reactions are going to be moles, molarity over seconds. First order is this, second order this, and nth order is going to be this. So we have to really, really pay attention to our units here. And I'll show you how to do that. All right. All right, so let's just take our numbers and let's figure out with just the numbers and not the units what our numerical value should be. Now, the way that we do this, solve for K, is you can take any one of these trials. It does not matter which trial because it's all going to give you the same answer. So let's just do 2 here. Just randomly pick 2. We're going to use this data for this trial to solve for K. All right, so remember, to solve for K, that's going to be equal to the reaction rate over the orders. So we're going to have our rate here over concentration of A to the first order, b to the second order. All right, so let's substitute in our numbers. We're just doing numbers here and not units. We're going to do the units separately. I like to do those separately. All right, so our rate is 0.020. And this is the easy part, by the way. Over concentration of A is 0.0080 times the concentration of B squared, 0.0040 squared. All right, so I didn't worry about this trial and not this trial. I mean, I could have chosen 1 or I could have chosen 3. Doesn't matter. We just chose 2. You just choose any one of the trials and substitute in these numbers. All right, so going to the calculator, we have 0.020. Let me make sure this is right. Yep. Over. Okay. 0.0080 times 0.0040 squared. Okay. Oops. Let's do that. Squared. Okay. All right. And so when we do the math here, we're going to get 1.6 rounds to the 5, 1.6 times 10 to the 5th. Okay. So this is going to be, oh, it's right here. 1.6 times 10 to the 5th. All right. So now we need to do our units. All right. So you're going to have to hang on. I'm going to show you this one time and show you how the algebra works for rearranging this. And then after that, you're going to have to remember algebraic rearranging. All right, so let's clear this off. All right, so up here in this corner, I'm going to rewrite. We have our rate over concentration of A over the concentration of B squared. All right, so now we're just going to do the units and nothing else. So for our rate, we have moles per liters per seconds. So we have moles per liter per seconds. All right. So I want to rearrange this and make this easier. So if we have a fraction, and let's make this a fraction, we have a fraction divided by this fraction, right? So if I wanted to not have this as a fraction, if I wanted to move this s over 1 up to this level, I'm going to have to do, let me see if I can remember how y'all say it. Switch, flip, I don't know. I'm going to have to multiply by the inverse. That's how I learned it. Keep, change, flip. That's it. Keep, change, flip. All right. So I want to keep this one the same. And I want to change this from dividing to multiplying. And I'm going to flip this one. So it's going to be 1 over s. So it's the same thing I said. Multiply by the inverse. Instead of s over 1, 1 over s. So I don't have to remember keep, change, flip. I just multiply by the inverse. All right, so that's going to get rid of this much. Okay, so now we have just a fraction times a fraction, which is a little bit simpler to deal with. All right, now this is going to be divided by moles per liters times moles per liters squared. So if we simplify this bottom here, okay, so remember when you are multiplying exponents, you're adding the exponents. Moles times moles squared is moles to the third. Liters times liters squared is liters to the third. All right, so now we've simplified this to this. So it's this divided by this. So we want to get rid of this fraction. Keep, change, flip. So we're going to keep this. We're going to change from dividing to multiplying. We're going to multiply by the inverse. Okay, so I'm going to get rid of this. So what's the inverse of this? Flip. It's going to be liters cubed over moles cubed. This is the hard part, is dealing with the blasted units. Numbers are easy. Okay. So we have this times this times this. So this is just like dimensional analysis. This times this times this. All right. So you remember, I'll always say what's on top cancels what's on bottom. So let's do some canceling out before we multiply. So here we have liters on bottom, liters on top. So this liter can cancel one of these liters, leaving 2 here. We have a mole on top that can cancel one of the moles that are on bottom. So we have a 2 here. So no seconds, so we can't cancel out any of the seconds. So what we have here is, this is really a 1. 1 times 1 times liters squared. Okay, so we have liters squared over, this is really a 1 when we cancel it out, 1 times S times moles squared. So we have moles, seconds times moles squared. All right. So here we have a fraction. Now, you could just leave this, but sometimes this isn't matching the units that you have in your answer. So see here, it doesn't match the units that we have in our answer exactly. So we need to get rid of this as a fraction and just make it all on the same line. So the way that we do that is, if you have something that has an exponent and it's in the denominator, you can pull it up to the top here, okay? But it's going to be the negative of this exponent. So this is now going to become moles to the negative 2, okay? So we got rid of it here. We could do the same thing with S. So this is going to be S to the negative 1, because 1 over S, which is what we have here, 1 over S is equal to S to the negative 1 power to get rid of this fraction. So now that we've moved those up there, we have, let me just erase this instead of cross it out, because that might be distracting. We have liters squared times moles to the negative 2 times seconds to the negative 1. So if I just rewrite that without having these multiply signs in here, I'm going to have liters squared moles to the negative 2 S to the negative 1. Okay, and that matches what we have for our answer. All right, so please, if you didn't get that and you didn't understand how to rearrange those units, please, this is algebra 2, right? Maybe it's just algebra. It's just algebra. Please go back, rewatch that, and make sure you remember those rules on rearranging that I just showed you. Okay? So that's it for 9.1. We're just talking about reaction orders, calculating reaction orders, calculating K, and calculating using information from trials to do all of that. So it's just the same thing over and over. So make sure that you have these notes. Make sure that you get how to rearrange this. All right, so thank you for watching. Make sure that you click that like button, slap it right across the face. Make sure that you subscribe so you know when I work out some sample problems and put them up on YouTube and you can watch those. And that notification bell will let you know when that happens.